Welcome to this event about integrated and sustainable retrofit solutions, adopting life cycle thinking principles. This event is organized by the FIB Italy Young Members Group in the framework of the CA Concrete Affairs webinar series. So the speakers from today are Simone Labò and Chiara Passoni from University of Bergamo in Italy. So about our speakers, Chiara Passoni is currently a postdoctoral research fellow at University of Bergamo. And before that, she was awarded her PhD at University of Brescia, and she was also a visiting student at University of Toronto. And she's an expert in performance-based design and life cycle thinking, and also construction sustainability, as the residual life assessment of existing buildings, and in general, holistic structural and energy renovation for existing structures. While Simone Labò, the second speaker of today, is a postdoctoral researcher at University of Bergamo. And before that, he was awarded the PhD still at University of Bergamo, and he also spent a research period at University of California, San Diego. And he's an expert in still life cycle thinking approaches, and also a numerical analysis and experimental campaign to investigate the use of such new retrofit solution, integrated retrofit solution for the renovation of existing reinforced concrete structures. So thank to our speakers from today, and thank you all for attending this event. And I would say the floor is yours, please.
So good evening. I'm just trying to understand how to share my presentation. I don't have the... Yes, okay. So may you see the presentation?
Yes, perfect.
Okay, thank you, sorry. So, good evening, everybody. So in this presentation, we are going to talk about integrated and sustainable retrofit solution adopting life cycle thinking principles. And we are going to present some concepts and results that we produced with our research group at the University of Bergamo. So it's well known that the construction sector is a very impacting sector and is responsible for the 50% of raw material consumption and 35% of waste production, 35% on energy consumption, and also 35% of greenhouse gas emission. I don't know if you noted it, but lately every seminar and every paper about sustainability of the construction sector just open with this figure and these numbers, and often happens that we are just so used to these numbers that we don't realize anymore what these figures represents, and that behind these figures, these numbers, we have real and tangible impacts that years after years spoil our environment, our landscape, our planet, and our health. So to make these numbers more tangible, I would like you to report some data about the construction industry impacts. Just to make an example, in Italy, the last year, 29 millions of cubic meters of sand and gravel were extracted, 26.8 million of cubic meter of limestone, and 3.6 million of clay, just to produce about 19.2 millions of tons of concrete, which is about 318 kilos of concrete per inhabitant. And this is just for Italy, and it's just for the last year. About the waste production, we know that C&D waste, so construction and demolition waste, is the largest waste stream in Europe, and in terms of mass. In EU 28 in 2016, 374 million tons were produced, excluding excavated soil. So considering that by 2020 it was set a recovery target of 70% of this kind of waste, it seems that we have a high level of recovery of this waste by construction and demolition. However, the high recovery of construction and demolition waste is often based to a large extent on backfilling or on low-grade recovery, for example, for road subbases and so on. In addition, we should consider that in Italy, a great part of the C&D waste is still not tracked, so data are not entirely credible, and the situation may be much worse than what appears. About greenhouse gas emissions and energy consumptions, we know that the residential buildings are responsible for a large share of greenhouse gas emissions in Europe. That are due to operational energy use, especially for heating, cooling, generation of hot water, lighting, and so on. But this is not the only impact of the construction sector on the environment, because we should consider that also the production of construction materials generates a great share of greenhouse gas emissions, especially for steel and concrete. So if we consider some 2012 data, we know that the steel and cement industries together accounting for 8% of global energy use and 15% of global anthropogenic CO2 emissions. And from 2012 to now, the steel and cement consumption are greatly increased. So the greenhouse gas emissions are surely increased, connected to just the steel and cement industry, not to consider all the other construction materials that we are using in the construction sector. So these are just some numbers, but I wanted to give you an idea that the impacts of the construction sector are something real and very tangible, and that all this is contributing to the global warming and climate change, and the effects of the impacts of the construction sectors on our environment are we can touch them with our own hands, and we can see them in each one of our cities. So now the point is, what can we do as engineers, as researchers, as designers to reduce the impacts of this construction sector? So now, considering the European strategies to reduce impacts of the construction sector, we are just focusing on the energy consumption of the buildings, and so to the greenhouse gas reduction connected to the energy consumption of the buildings. A BPIE report of 2020 just say that in order to reduce the greenhouse gas emissions and to reach the climate neutrality of Europe by 2050, we really need a strong interventions on our buildings in order to reduce their emissions. They compare two different strategies and two different scenarios, and they notice that the only way to reach climate neutrality by 2050 is what they call a responsible policy scenario, in which we have to shift to 53% of the use of renewable energy and reduce the consume of fossil
45%.
Of fossil energy by 47%. And we cannot reach these ambitious targets if we just think to construct new eco-efficient buildings, but we need to renovate the existing building stock. So what they say is that in order to reach such ambitious goals, we have to shift from the actual deep renovation rate, which is equal to 0.2% per year, to 3% per year, which is a medium value between 2015 and 2030. So since we are in 2021, we need to increase the deep renovation rate at least at 4.4% on average in the decade from 2020 to 2030 in order to reach the climate neutrality of Europe. But even though this is a great ambitious goal, we are not considering which will require great energy to and great policies to reach such goal. We are still not considering some impacts which are very important, and we are not considering that two important issues among others. The first one is that we are, when we are building new energy efficient buildings, or when we are renovating the existing building to have such a good performances other than energy point of view, we are at the same time increasing embodied energy. So the energy that the building consumed during the production and the construction of the building or of the intervention, and at the end of life. So what we have to do is to make a balance between operational energy and embodied energy in order to reduce the global energy consumption and greenhouse gas emissions of our buildings. Otherwise, we're not going to reach our targets because this embodied energy is too high, and it just don't have any importance that we are reducing operational energy if we have high embodied energy. So we have to reduce the energy consumption and greenhouse gas emission considering all the building life cycle. In addition, we have just seen that in order to reach our goals to reduce energy consumption in existing buildings, we have to renovate the existing buildings. So another very important point when we're going to renovate existing building is to consider also the other deficiencies of existing buildings, especially the ones connected to the structural vulnerability against hazards, and especially against seismic actions. So what happens when we evaluate the energy interventions, the interventions aimed at reducing energy consumption, and we re-evaluate them also considering the presence or the possible occurrence of an earthquake? What happens is that we have indeed a longer payback time with respect to that we attended, and we also have higher impacts on the life cycle. And these impacts and this payback time just increase as the seismic risk increase. And what can happen is also that in case of very strong earthquakes, we may also have the collapse of the building, and this will just cause the total loss of the investment, and at the same time we could also have the loss of human lives. So with this in mind, it's possible to understand how the actual strategy to reduce construction impacts and greenhouse gas emissions by just reducing the energy consumption of building in the use phase is not enough. A renovated building just under an energy point of view is such a great missed chance to improve our obsolete building stock in a wiser manner. So we can do much more, and what we can do is just to approach the construction industry, the building renovation, the study of new structural systems, or also the study of new construction materials, just adopting a new approach, which is the life cycle thinking approach. This approach is an approach that goes beyond the sole operational stage of the building, it considers all the stages of its life cycle. So product stage, construction stage, your stage intended as maintenance, your stage intended as behaviors against hazards, end of life stage, and also beyond end of life stage, so reuse, recovery, and recycling of the materials. This kind of approach, the life cycle thinking approach, may be applied in our project, in our researches, considering two methods. The first method, which is the most applied, is to adopt the life cycle thinking by adopting life cycle tools, which are life cycle assessment analysis or life cycle cost analysis, which are some analysis and tools that allows to calculate and compute all the impacts, all the costs along all the building life cycles, considering all the stages, evaluate the input and the output of our building, and compare different alternatives, or make a ranking of these alternatives on the basis of the results of this analysis. But what we are doing in this case is the ranking that we obtain is just a ranking that may select the best options, but among options that may be also even very impacting on the environment, or they may be all very expensive solutions. So we are not sure that the building or the solution or the alternative that we are selecting with these methods is just a sustainable alternative, because maybe it's the best among the worst. So what we should do to really adopt a life cycle thinking approach is to shift our consideration at the beginning of the design stage. So introduce a first step before the design and introduce new life cycle thinking principles, which are principles aimed at reducing costs and impacts along the whole building life cycle. And applying this life cycle thinking principle, we may either reevaluate the existing solutions and select only those solutions that are compliant with these life cycle thinking principles, or we can just conceive new solutions that are compliant with life cycle thinking principles. So selecting these alternatives which are compliant with life cycle thinking principle, we can adopt the life cycle assessment and life cycle costs to estimate the impacts along the life cycle in a second step of the design, at the end of the design. But in this way, we are sure that our solutions are all sustainable, and we are just selecting the best one according to a series of criteria, but it's the best among the best choices that we have in terms of sustainability and impacts reduction. So, but what are these principles? So what are these life cycle thinking principles? We saw that life cycle thinking principles are principles that are aimed at controlling performances, impacts, and costs along all the life cycle of the building, and are aimed to pursue sustainability, but also resilience and safety. So just let's consider all the phases, all the stages of the building life cycle and define this life cycle thinking principle. So considering the product and construction stages, we would adopt sustainable, eco-efficient materials, just produce with low impacting processes, and possibly adopting recycled or reused material, according to the principle of circularity and circular economy. More, we should use dry solutions and prefabricated solution aimed at reducing the time of construction, impacts, costs, and risks connected to the construction site. In addition, we will just prefer renovation of existing structures to demolition and reconstruction, in order to reduce the amount of C&D waste and exploit the greater bank of construction materials that we have in Europe, which has been shown to be the existing building stock. In addition, considering the use phase, there's not just the adoption of energy upgrading measures to reduce the impacts of the buildings during the use phase, but we should also consider some other phases. For example, we saw the possible presence or the possible occurrence of earthquakes. And in this case, we need to design our solution from the beginning in order to reduce the damages on our buildings in case of earthquakes. So what can we do is just to design some solution that lump damage into replaceable fuses, which can be easily replaced after an earthquake, or to consider demountable techniques in which it is easy to replace some damaged elements. In addition, we can consider new performance objectives and structural targets aimed not just at saving lives and prevent collapse, but also at reducing damage to structural and non-structural elements and losses, even for high-intensity earthquakes, as you will see in the last part of this presentation with my colleague. Also, solutions and techniques should be designed in order to guarantee the maximum flexibility and adaptability along the building life cycle. So easy substitution of some elements if and when it is required. This is possible considering, for example, standardized connection or interchangeable elements and so on. Thinking about the end of life of the building, we should consider to we should think to the end of life of our building from the beginning of the design of our solutions. So we should consider dry solutions, demountable solution, which may be easily demounted and dismantled from the building, and materials that can be recycled, and techniques that can be reused, elements that can be reused in other buildings for the construction of other buildings, for example. Finally, as a final aspect, since we saw that the major greenhouse gas reduction will come from the retrofit of existing buildings, we should also consider retrofit intervention from the beginning to overcome the barriers of the renovations, because we saw that the renovation rate is too low and we need to increase it if we want to reach the European targets in terms of emissions, so carbon neutrality in 2050. So we know that the major barrier to the renovation is considered the inhabitants' relocations. For this reason, additional exoskeleton techniques have been proposed to enable a holistic, so structural, energy, and architectural renovation of the existing buildings. What are exoskeleton? Under a structural point of view, such exoskeleton may be realized in two ways. By considering some wall solutions, so by lumping the strength and the stiffness of the structural intervention into few elements that may be realized with different technologies, and walls that may be perpendicular to the building, just like that, are encased in a new skin of the building, or they may be also in adherence of the existing building, like in this example here. Or we can also do some shell solutions, so to solutions that exploit the length and of the facade and reduce the dimensions of the substructure or the structural element both in the substructure and in the foundation system. And this system may be realized, for example, with diagrid exoskeleton or with wooden additional skins. So in order to show you how this principle may be used and considered at the beginning of the design of the structural solutions or in general retrofit solution, in order to be compliant with the life cycle thinking approach and to use these principles to conceive new solutions that are compliant with the life cycle thinking principles, I just show you an example of a holistic retrofit solution which was conceived to be compliant with life cycle thinking principles. This is the ADESA system that the University of Bergamo studied with the University of Brescia and with our other commercial partners, so Marlegno, Arpaceas, and Edilmatic. And in the context of a regional grant on smart living. And what we propose is the system consists in a new wooden envelope for existing buildings, able to improve the seismic and the energy performances of the building, but also the architectural layout. The system is realized by adding to the existing layer of the building a new structural layer, a new thermal layer, and new architectural layer that may vary from building to building. The system, as I told you, is conceived to be compliant with life cycle thinking, so it is applied from the outside in order to overcome the barriers to the renovation, and it is also conceived to be compliant with the principles of prefabrications and easily mountability of the system. So all the elements of the system will be produced and assembled off-site and just shipped and mounted on the construction site in order to reduce the impacts of the construction sites, the risks on the construction sites, also the time of construction. In addition, the connections were studied in order to reduce the damage in case, to lump the damage in case of seismic events. So all the damage will be lumped into these elements of the connections, and they may be replaced after an earthquake. In addition, these connections among the elements of the skin and between the exoskeleton and the building are conceived to allow for the selective dismantling of the system. And in addition, all the layers of the system are conceived to be recyclable and reusable at the end of life. So this system was applied to a gym hall in Brescia, which is a city in the northern Italy. It's an ex-seismic zone 2 and it is a climatic zone E according to the Italian codes. And there is a system allowed to pass from an energy class E to an energy class B, from a seismic class F to a class A. The construction cost of this pilot projects was of 380 euros per square meter of shell. And the construction time was about 4 or 5 months, excluding the stop due to the COVID pandemic. Many other applications of the ADESA systems will be realized in the next months, also thanks to the super bonus. So we will have soon some more data about this solution and the efficiency of this solution. So just to conclude this first part of the presentation, I hope that you have understand that when the life cycle thinking approach is adopted to conceive retrofit solutions for existing reinforced concrete buildings, the advantages in the reduction of the impacts and on all the whole life cycle of the buildings are evident. So suppose to have this building on the left. and supposed to consider 3 different retrofit scenarios that leading to the same performances of the building at the use phase. So for example, a reduction of the 60% of the operational energy, and that will lead to the same seismic performances, for example. When we consider demolition and reconstruction, what we have as impacts at the construction phase is the impacts connected to the demolition of the existing building, and all the impacts connected to the construction of a new building, which will have higher embodied energy than the previous one. And at the end of life, we need to demolish all these buildings that we have generated. So if we consider on the other side, not LCT-based techniques, for example, let's imagine to strengthen all the nodes of these buildings. In this case, we may have the impacts connected to partial demolition of the buildings, at least of the finishing. We will have the impacts connecting to the production of these new materials, the production of the new finishes, and all the impacts of the construction site. Also in this case, we will have additional embodied energy, and at the end of life, we will need to demolish these buildings, and it's not guaranteed that if we use these techniques, for example, if we use node strengthening, we cannot recycle this material and we cannot reuse this system. On the other hand, when we use Lifecycle thinking-based techniques such as the ADISO system, but all the systems that are conceived from the beginning to be compliant with LCT principles, the impacts on the environment will be very reduced. So for example, we will have just the impacts connected to the production of the system, which is optimized to and studied to reduce the waste and the impacts at the product stage, at the construction stage. And then at the end of life, we will have the demolition of the existing buildings. We cannot avoid it. But the system that we have added to the building to make it energy and seismic resistant, all these elemental materials may be reused or recycled because they are thought to be reused and recycled. And so they will be reused and just with the principles of the circular economy. So that's reducing the impacts on the environment. In addition, we should consider another thing, that the first two systems necessarily requires the relocation of the inhabitants. So very often, as we've seen in the first slides, these systems are not realized. So we don't even have this improvement of the performance in the operational phase. So in this first part of the presentation, I hope to have increased your awareness on the impacts on the construction industries, which are real and which are tangible. And I show you the possible way to reduce those impacts through the life cycle thinking approach, and how its principles may be adopted to renovate existing building stock to make it truly sustainable. And that's may be done in all our researches, in all our projects, everything we are doing for the construction sector. And as for the renovation of existing buildings, especially existing reinforced concrete buildings, I have introduced to you the exoskeleton, and which are conceived to be compliant with life cycle thinking principles, and which are conceived to overcome the barriers of the renovation. So in the second part of this presentation, now I just leave the stage to my friend and colleague Simone Labò, which will show you some tools and some new design targets to design this structural and holistic exoskeleton. So thank you. So Simone, the stage is yours.
Thank you, Chiara Passoni, for the introduction, and thank you, Marta, for the first introduction. share my presentation. Okay. Okay. Can you see my presentation?
Yes.
I do. So yeah, okay. Thank you. And I begin the second part of the webinar using what Chiara has just presented and has just said, that different technological applications have been already proposed. And what we would like to show here is a new tool for the preliminary design of this retrofit solution. And the objective of this second part of the presentation is to introduce a tool that allow us to have an idea on what the minimum stiffness of the retrofit should be to get a set design target. And to do this, starting from the preliminary consideration made by other research works in the last year, we are representing our retrofitted system through a simplified 2-degree of freedom model. We can see here the pointer. Okay, we can see here the simplified 2-degree of freedom system, in which the element 1, described by means of the mass M, the stiffness, the elastic stiffness K1, and the damping coefficient C1, represent the existing building, while the second element, defined through the mass M2, the stiffness, the elastic stiffness K2, and the damping coefficient C2, represent our retrofit solution. The two elements are connected by an elastic spring and a damping element. And in this case, today, the only one nonlinear behavior is introduced for the existing building, which is represented through an elastic, perfectly plastic bilinear curve defined through the elastic stiffness, the yielding force, and the yielding displacement. I'm not going deep in the analytical aspect of the problem, but I have to introduce 3 parameters that are needed to read the design spectra I'm going to present. And these 3 parameters are required to be sure to be in the same page when the design spectra are presented. The first parameter is the strength parameter, which is represented through the symbol eta, and is obtained as the ratio between the yielding force of the existing building of the element 1, that means the existing building, and the elastic force to which the existing building would be subjected. To be clear, lower values of eta represent weak buildings. So eta equal to 0.3 represents a weak building, while eta equal to 0.85, so high values of eta represent strong building. The other 2 parameters are required to read the output of the design spectra. These are the ductility demand, mu, which could be obtained through the ratio between the maximum displacement to which the existing building experienced by the existing building after the retrofit, divided by the yielding displacement of the existing building. What does it mean? This represents the ductility demand to the existing building after the retrofit. Higher displacement required to the existing building means more damage to the existing building, and we translate this aspect with high values of mu. And the last parameter is the retrofit stiffness ratio. Is indicated with lambda tilde, and it is expressed through the ratio between the elastic stiffness of the retrofit solution and the elastic stiffness of the existing building. I'm not going deep in the connection problem, but the tilde, remember us that the retrofit is composed by both the connection and the exoskeleton. Today, we are considering the connection as rigid, and for this reason, the stiffness, the global stiffness of the retrofit is equal to the stiffness of the exoskeleton. So these are the three parameters that we need to read the design spectra, to understand what design spectra say. The first one is the strength parameter and refers to the existing building, to the capacity of the existing building. The second one is the ductility demand after the retrofit. The ductility demand required to the existing building after the retrofit. And the last one is the retrofit stiffness ratio. I'm going to leave these three parameters in the bottom of the slide just to allow us to keep in mind. And given these three parameters, and under the hypothesis that the connections are rigid, as I already said, and the retrofit mass is lower than the existing building mass, we can derive the design spectra. Design spectra are derived by solving the equations of motion of the simplified system described before, in this case in MATLAB, and through the equation solver ODE45. As I said, I'm going to skip the analytical aspect of the problem, but this is an example of design spectra. What design spectra plot? In figure, we can see that the ductility demand, and to understand the displacement demand on the existing building, is plotted as a function of the stiffness of the retrofit solution, indicated with lambda. For example, for a fixed existing building, and it means that for fixed yielding displacement of the existing building and for a set stiffness, elastic stiffness of the existing building, we can plot through the design spectra the displacement demand required to the existing building after the retrofit as a function of the stiffness of the retrofit solution. And the objective and the goal of the spectra is to define the minimum stiffness required to reach a set design target. And the design target is expressed through the mu parameter. But let us discuss on this result. What we can see is that for lambda equal to 0, we have the existing building in the as-is situation. At this point, corresponds higher values of mu. So if I do not introduce the retrofit, damage on the existing building are higher. It's reasonable. But introducing a retrofit solution, I can see that damage are at the same the same time, the displacement required to the existing building after the retrofit decreases. And what we can see is that by introducing a retrofit solution, a significant decrease of mu is observed, while to further reduce the displacement under, for example, values of mu equal to 1, higher stiffness is required. Or again, for a set value of mu, for example, in this case, mu equal to 1, increasing or decreasing the strength of the existing building, so decreasing eta from eta equal to 0.85 to 0.3, the required stiffness increase to reach the same design target imposed as equal to mu equal to 1. At the same time, for a set value of lambda, increasing the value of eta, the ductility demand on the existing building decrease. But let's focus on the objective of the design spectra. Design spectra allow us to derive the minimum or the required minimum stiffness of the retrofit to reach a set design target for a fixed value, for a set value of eta and of the elastic period of the existing building. And this is the main aspect, the main objective of this spectra. And what we can say is that this spectra can be applied to all the retrofit solution presented before, both shear wall or shell structure can be designed, preliminary design, by using the design spectra. But not only for spectra cannot be only used for the preliminary design, but also they could be integrated to make, for example, consideration on large scale, or for example, they can be combined with energy analysis or loss cost analysis. What we would like to do here is to summarize some of the main aspects presented in the first part of the webinar and in the second part. So what we would like is to propose a design procedure based on the definition of new performance objectives, considering the whole life cycle of the existing building, and design a new retrofit solution based on these performance objectives by using the design spectra presented here. The proposed design procedure is developed on 5 steps, and the first one is the easiest one, because in the first one we have to identify the building features, and what we can do is just to follow the procedure proposed by the current codes. The second step is a key step, because we are going to introduce new performance objectives and consequently new design targets and operative choices to consider the whole life cycle of the retrofitted building. In the third step, we will apply the design spectra. We will use the design spectra to derive the minimum stiffness K. And finally, we define a layout of the retrofit. We are going to choose one of the exoskeletons presented before, and we validated the procedure through a finite element model. As I say, the first step is what in the first step, we follow what we do for a normal vulnerability analysis in which the bilinear curve is derived and the yielding force, the yielding displacement, the fundamental period, and the stiffness of the equivalent single degree of freedom system are derived. And in the second point, in the second step of the design procedure, what is important to note here is that to foster sustainability of the renovation process, a new multi-criteria approach that consider the whole life cycle of the retrofitted building should be considered. And with this aim, or when a life cycle perspective is considered, new design targets should be introduced. And should be introduced to account for an environmental sustainability, life safety and structural feasibility, and social and economic sustainability. But what does it mean? For example, to consider environmental sustainability, we have, for example, to avoid damage on displacement and acceleration sensitive elements in order to guarantee the operability in the case of the design earthquake. Or, for example, to reduce the repair cost and impacts in case of life safety earthquake. Because if we have to demolish, the retrofit solution after the life safety earthquake, probably this will not be an environmental friendly solution. As for the life safety and the structural feasibility, we have, for example, to avoid the overload of the existing foundation system or of the existing floors. And as for the collapse prevention earthquake, we have to activate, for example, dissipative devices to allow a ductile behavior at the collapse prevention earthquake. And finally, as Chiara previously said, as for the social sustainability, we have to avoid the relocation of the inhabitants because it is one of the major barriers to the renovation. During the construction of the retrofit solution, and later after for example, the ground motion of the design ground motion. And this aspect can be translated into performance objectives that could be synthesized through the operational performance objective for the life safety earthquake, or for example, the life safety performance and the ductile behavior for the collapse prevention earthquake. I'm not going in deep now on the target required to satisfy these performance objectives, but what I would like to underline and what I would like to highlight today is that we have to shift from what the traditional approach used to do. We have to shift, for example, to guarantee the operational performance objective, not only for the occasional earthquake probability, but also for rare earthquake probability. In the third step, we are going to see how to apply design spectra to derive the minimum stiffness required to satisfy the imposed target, that is 0.3%, imposed to avoid the damage of the non-structural elements. To this drift target correspond top displacement equal to 75.6 millimeters, that divided by the yielding displacement and by the participating factor equal to 1.4, we obtain a value of mu equal to 1.5. And I remember that mu is the ratio between the maximum displacement experienced by the existing building after the retrofit and the yielding displacement of the existing building. So through this ratio and with these values of mu, we are getting that the required minimum stiffness to satisfy this target is correspond to a lambda equal to almost 1.3. That means that the stiffness of the retrofit should be 1.3 times the stiffness of the existing building, and only introducing a retrofit that has a stiffness higher than 1.3 times the stiffness of the retrofit of the existing building, we can reach the target imposed. And what is important to note here is that if we use the a less strictly target, for example, 0.5% to avoid I don't know, damage or failure of non-structural elements, we could use a very lower values of stiffness. And this gap represent how important is to consider the whole life cycle of the existing building and what are the consequences on the retrofit solution change of the perspective from the design, considering only the structural aspect, to the design considering the whole life cycle of the existing building. As for the definition of the layout of the retrofit, we are focusing today on die-grid structures. Die-grid are structure introduced in the last year for tall buildings and developed their bearing system by using through the triangular modules that are represented by two diagonals and one horizontal prefabricated elements. But why we choose die-grid for today? Because they are suitable in the integrated renovation. Because die-grid could be used to remove barriers to the renovation, being assembled from the outside of the building, and because they could be realized through dry solution, thus reducing the duration of the impairments at the construction site, and because they are compliant with the life cycle thinking principle previously presented. I'm gonna go to the validation through the finite element model. What we can see is that there is a die-grid that satisfies the design, preliminary design through the use of the design spectra for a design target equal to 0.3%. In this case, it's realized as an enlargement of the existing building to add additional living spaces in each floor of the existing building. And what we can see in the capacity curve is that in the weakest direction is that the performance objectives are satisfied. I've reported here just the pushover curve, but all the targets imposed were satisfied. And the infill cracking, that was the main objective of the preliminary design, is satisfied at the life safety limits state. To summarize what we have seen today, the problem statement, the first point is that we have to change our perspective to target sustainability, safety, and resilience at the same time in the building sector. In the first part of the presentation of the webinar, a new life cycle thinking approach to rethink the traditional construction system has been introduced. In the last years, our research group tried to adopt this approach to propose new techniques for the structural renovation of the existing building stock. While in the second part of the presentation, Design Spectra as a tool for the preliminary design of this solution carried out from the outside has been presented. What we would like to report also and underline also is that Design Spectra can be a useful tool for the preliminary design of the solution, but could be also easily integrated into, for example, large-scale analysis or sensitivity analysis that consider the integration with energy aspect or, for example, loss cost analysis. And we would like to conclude our presentation through these very powerful three points. The impacts of the construction sector cannot be ignored, and all of us are responsible for this of the state of our environment. Adopting a life cycle thinking principles, new structural systems and retrofit techniques have to be conceived aimed at reducing the impacts of the construction, but also many other solutions still need to be discovered. But more important is that now it's time for all of us to take action as to improve the sustainability, the safety, and the resilience of our construction. Thank you very much for your kind attention. I'm just making some sponsor to our, if you are interested, we are discussing on this aspect with other two seminars that we are going to do in the middle of June, I'm sorry. And for any information, don't hesitate to ask. Thank you.
Thank you very much, Simone. Thank you also to Chiara for your very nice presentation, super clear and also really interesting, also because the topic is super hot. So we are talking about, yes, when we talk about sustainability and integrated solution for existing structure and renovation, which is one of our current needs, it's always interesting to know and listen new perspectives. So if from the audience there is any question, you can write in the chat and I will read them for you to the speakers. So don't be shy. If you have any kind of question, you can use the chat. Meanwhile, maybe I can do some question for you. So which is the next step? So after this kind of solution, do you already see the future of this kind of applications?
So what we think is that now we are studying other solutions. So to renovate our existing building stock. So not just that there's a system that we saw, we are trying to apply it, but also to study other solutions that integrate energy and seismic renovation. And also we are just trying to study some new design framework in order to try to include all these principles at the beginning, at the design phase, as I was telling you, and maybe a new framework that allow the designers to make more some choices that are more sustainable and make them more aware of the choices that they are doing. So we are studying it, so how to select the best strategies to renovate existing buildings, depending on the building characteristics, on the site characteristics, but also on the customer requirements and so on. So how to consider all these criteria all together to select the best retrofit option from the beginning of the design. So it's
okay, thank you. And I don't know if Simone wants to add something or.
No, I think that what Chiara said is perfectly correct, and probably is important to know that this, as you say, this is the beginning of our research field, because a lot of research still need to be done to improve, to derive new tools for the best design, because we think that this is the future of the renovation of the existing building, and this is the way we propose, not the only one, of course, but the way we propose to reach the ambitious target that Europe and the world proposes.
Okay, great. So I don't see any kind of question in the chat. So probably you were too clear. And so people totally understand everything and they don't have any other questions. So if you want to ask or get in touch with the speakers, you have their contacts, and the event has been recorded. So you will find this the video on our YouTube channel of the FIB Young Members Group in Italy. I think in a couple of weeks, so you can find there, and see again the video, and also, contact Nicola or Chiara. And also, if you are more interested in joining, you said these 2 other seminars are free of charge, right? So people can join from any university or institution without any kind of fee. Perfect. So that's super good.
Yes.
Okay.
But they are a little bit more than a seminar because they are a little longer, but this topic will be analyzed.
Yeah, so a sort of a course, a short course about how to approach design and of such retrofit solution. That's good. Are you thinking also to do some induction for practitioners? So do some courses for people in industry that actually design and do renovation also in this framework of new bonus systems in Italy? I don't know.
We are thinking about that, and we have a project that we are developing. It's under working.
Okay, we have a question in the chat from Simona Bianchi. So thanks for the interesting presentation. So which type of multi-criteria method are you using for your investigations?
So,
this is the focus.
At the moment, we are analyzing some multi-criteria decision-making tools to select the best options. So in the paper that we already published, we considered the TOPSIS method and the procedure that was proposed by the professor Nicola Caterino. But we are that allows us to make some qualitative comparison among the alternatives. So also consider qualitative criteria, because if we want to anticipate this analysis at the beginning of the design process, we don't have indication about the cost, for example, or the impacts, so that we can analyze them. So we are trying to use some qualitative criteria, and so to use this decision-making tool that allows to consider qualitative criteria. But now we are also working on different tools, so in some way to change these systems to make this comparison easier. So we are just inventing a new multi-criteria decision-making tool, which is inspired by the existing one, but a little bit easier and more intuitive to use. So stay tuned. And we are going to publish even this system. But you can find it if you're interested and you want to have some of our publications. You can write me and I can send you the papers, so you have all the indications.
Great, thank you. There is another question. So are you aiming to at development of standardized design spectra?
That's my turn. Thank you, Simona, for the question, because this is a topic we are dealing with, because spectra, as you correctly said, are not standard, because they depend on the elastic period, for example, or the strength. And we are working on that, but more of the, not only on the standardization of the design spectra, because it's very hard to start to eliminate the dependency on, for example, the elastic period or of the strength of the existing building. But we are trying to make this tool easier to use, to be used for the preliminary design. We are trying to generalize the solution in order that this could be used for different buildings. So avoiding the dependency of the elastic period and of the, for example, of the site, because also the ground motion used affect the response of the spectra. We are trying to make a tool easiest to be used, so in which you can introduce only the parameters of the existing building and you can get the stiffness required. So I'm not sure we are going to standardize the spectra because it's hard to do, but we are trying to make the dependency of the parameters less influent, or maybe less an issue to get the minimum stiffness. We are working on it. Thank you.
Perfect. Thank you very much. And I don't see other questions in the chat, so I think it's okay. Thank you from Simona. Great. So I want to thank you again for your time and for your kindness in sharing your experience and knowledge with us today. And thanks also to the audience for the questions and also for being here with us. And please continue following our events for the future, and have a good evening and goodbye. See you soon.
Thank you. Goodbye.
Thank you.